Uh, Welcome everybody to the ArcScience seminar, and it's a great pleasure today to have an old friend, Hugh Thomas, from the University of Quebec, Montreal, and he's going to talk about the Robinson-Schensted-Knuth correspondence via quiver representations. Hugh, over to you.
Thank you, and it's a real pleasure to be speaking to this audience, and thank you all for coming, and thank you to the organizers for the invitation. Thank you, Omri. So I'm going to be talking about some work with Garver and Becky Patrias, largely, really just what's in these two papers. So this is the archive paper, and then the second one was the FIPSAC abstract from a few years ago, which is more condensed, but also focuses more on the combinatorics. So if that's the end of the story that you find more appealing, you might find that a more, you might like to start there if you wanted to look at these papers. With that, right, okay. So I'm going to go over some background that will be familiar to lots of you, but let me just quickly go through it. And please don't hesitate to interrupt or raise a hand or speak up if you have questions. So the oh goodness, if you're following my video that is that you're focusing, that Zoom thinks you should be focusing on, you're seeing me kind of on one side and cut off. But there is another video where you see me right way up. Ah, super. Thank you, Omri. Sorry, now I'm getting a warning about it on my other screen. Okay, so super. Right. So some basics. Partitions, just sequences of weakly decreasing numbers. N is the sum. We say that lambda is partition of n. We write lambda as partition of n like that. The length is the number of parts. Ferrer's shape. I'm using despite the fact that I'm at a Francophone university, I learned about these things to begin with at the University of Chicago. And so I use the Anglophone convention, which is that when you have a partition, then you represent it as a sequence of, as a diagram of boxes with the first entry giving you the first row, and then the second entry giving you the row below that, and so on. Whereas the Francophone convention would reverse that, and you would have the row of 4 boxes, and then above that the row of 2 boxes, and above that the row of 1 box. Anyway, so I use the English convention. So we're going to need a few different kinds of fillings of these shapes. So we're just going to be filling them with. So in an individual box, we're going to put in one positive integer, typically. So a semistandard Young tableau is a filling where it's weakly increasing along rows and strictly increasing down columns. So here's my example. It has to strictly increase down columns weakly across rows. A standard tableau is the same, but the entries go from 1 to n. So that means that automatically it's strict in both directions because there are no repetitions at all. A reverse plane partition is the same thing again, but the entries weakly increase along both rows and columns, and 0 is allowed. I should have said that. So there's a classic procedure. So I'm going to be talking about a new version or a new way of thinking about RSK, and so I wanted to define classic. Well, I'm not going to define actually classic RSK, but I'm going to define the classic Robinson-Schensted correspondence just to make sure we're all on the same page. And so to do that, I'm going to define Tableau Insertion. So this is a procedure that, given a tableau and a number, sort of sticks the number into the tableau, but it also rearranges the entries of the tableau. And in the end, you have a tableau that has one more box. So to insert an I into a tableau T, we begin by looking at the top row, and we put I in at the reasonable place in T, and it turns out that the reasonable place is the rightmost place that it fits in that first row. And if that's the very end, then we just put it of the row. Then that is to say, if it is greater than or equal to everything that's already in the row, then we just put it at the end, and that's fine. But if not, then we want to put it somewhere where there's already some other number. And in that case, we view that number as having been bumped out, and then we have to insert that number into the next row. And so then that may bump out a number from the second row, and then we have to insert it into the third row, and so on. But at some stage, we'll be able to put the number down at the end of the row, and then we'll be done with that insertion process. So to give an example, let's say we were trying to insert a 1 into this tableau. So we look, where can we insert the 1? And so this is where the 1 wants to go. So we put it there, but that bumps out the 2. And so now we have this 2, which we're supposed to insert into the second row. And again, that the place it wants to go is there. So it bumps out the 4, and we have to insert the 4 into the third row. The third row is empty, but that doesn't really make any real difference. It just means we insert the 4 there, and now that's great. We're done, because there wasn't anything there before, so we didn't bump anybody out. We just insert the 4, and there we are. So that's the result of Tableau insertion. So I can now define the Robinson-Schensted correspondence. So there's a bijection from permutations in Sn to pairs of standard Young tableau of the same shape, and that shape is a partition of n. So we're sending a permutation to a pair of standard Young tableau. P is called the insertion tableau, and Q is called the recording tableau, and for reasons that will become clear. So to construct the tableau P, we first insert the first entry of the permutation, then we insert the second entry, and so forth. So we just work our way through the entries in the permutation, inserting them, and the resulting tableau is P. And to construct the recording tableau, we just keep track of the way that the shape of P evolved as we did this. So we put a 1 in the box that was added at the first step. Then we put in a 2 at the box that was added at the second step, and so on. Okay. So to just have an example of that. So this was the rules again. So let's say my permutation was 1 goes to 2, 2 goes to 3, 3 goes to 1. So we first insert 2. Then we're going to insert 3. So it winds up there. And then we're going to insert the 1. The 1 bumps out the 2. Then we're going to insert the 2 into the second row. It winds up there. So this is the resulting insertion tableau. If we look at the recording tableau, we see that first we added this box. So we put a 1 there. At the second step, we added this box. At the third step, we added this box. Notice that isn't the box that we first inserted into, but it's the box that got added at this step. You know, the 1 went to the 2, that bumped out the 2, the 2 wound up there. So this was the box that was added, and that's what we record in the recording tableau. So so there we are. We get the insertion tableau and the recording tableau. And that's the Robinson-Schensted correspondence. And if you think about it, you can convince yourself that it's invertible. If you had a pair of standard tableau of the same shape, then you would be able to invert it, because you look in the recording tableau and you see where is the number n. Well, I mean, it's a standard tableau, so there must be one instance of the number n. In this case, it's here. And so that tells you where the insertion process, where the final insertion process ended up. So we ended up with this 2. So then you can reverse the insertion process because you say, oh, I ended up with this 2. Well, the 2, that means that I was at this stage inserting the 2 into this row. Well, how did that happen? That happened because, must have happened because 2 was up here. Well, 2 was up in this row and it got bumped. But where in this row was it? Well, it had to have been here. So it must have been bumped by 1. And so in a taller tableau, we would then have to say, oh, okay, so we had a 1. So that must have come from the previous row. And then we would keep going like that. In this case, we already have figured out, oh, this must have been because we were inserting the 1 into the first row. So that was the last entry in pi was a 1. And so we can conclude that at the previous step, we were here. And so now by induction, we can keep going. We can peel back off the entries to and reconstruct pi. So that's Robinson-Schensted, and that's it's a bijection. So the thing that I'm going to be talking about today is a generalization of that. It's and it's somehow it's more naturally it's more natural to think about the way that I want to do it. It's more natural to think about it in the Robinson-Schensted-Knuth this more general setting. So I do want to explain kind of how that setting works, but I'm not actually going to give the full definition of RSK in that setting unless somebody insists. So RSK is a bijection, which I'm going to think of like this, as a bijection between non-negative integer m by n matrices and non-negative integer reverse plane partitions of the same shape. Okay, so recall that reverse plane partitions are weakly increase in both rows and columns, which is somehow not. You can transform RPPs into standard Young tableau if you want, but somehow this is the formulation that's more natural. So this, on the face of it, doesn't look so much like Robinson-Schensted, but Robinson-Schensted is down here. It's this correspondence. And so the ingredient that sort of, there are several ingredients to turn RSK into Robinson-Schensted. One is, if we have a permutation, we can think of it as a permutation matrix, and that turns a permutation into a very particular kind of matrix. In particular, I need to assume that m equals n. But so then a permutation gives me a matrix. How about a pair of standard Young tableau? Well, a thing that I can obviously do to generalize a pair of standard Young tableau is to say I could have a pair of semi-standard Young tableau. And that's in fact what we want over here. And it turns out that reverse plane partitions correspond bijectively to semi-standard Young tableau. Sorry, reverse plane partitions correspond to pairs of semi-standard Young tableau of the same shape. And so let me explain how that works, both because it's kind of intrinsically sort of interesting, and also because it's a bit relevant for the other things that we're going to have to do with reverse plane partitions in the course of this talk. So if you have a reverse plane partition, such as this guy over here, how would you turn that into a pair of semi-standard Young tableau? Well, what you do is, as the first step, you split it along the main diagonal. Okay, so here's the main diagonal, and we turn it into just the part that's below the main diagonal and the part that's above the main diagonal. And we repeat the main diagonal in both of the two parts. Now, what are we going to do? Well, if you think about it, when you look along the main diagonal, you see, obviously, well, if you read it upwards, then you see a weakly decreasing sequence of numbers. So you can view that as a partition. So you can view this reverse plane partition as specifying a series of partitions. And, so the first one having at most one part, the second one having at most two parts, and the third one having at most three parts. And the inequalities on the entries of the reverse plane partition are exactly such as to make this what is called a Gelfand-Sutton pattern. And without using a fancy term, that is exactly what you need to make sure that these partitions are contained one in the next. So, and in exactly the right way, so that if we view the first partition as telling us where the ones go, and the second partition as telling us where the twos and ones go, and the third partition is telling us where the threes, twos, and ones go, well, so then the result will be a semistandard Young tableau. And that perhaps requires a little bit of sort of playing about with to get one's head around. But once one's used to the idea, it turns out that this is a very nice way to encode a semistandard Young tableau. It's somehow, I mean, in this case, it doesn't look like it particularly, but this way of thinking about it is more compact often than this, because you don't have these long strings of the same entry repeated over and over again. You're just kind of keeping track numerically of where things end, and this where the strings start and end, if you like. And this this version is one in which you can start thinking of the kinds of Tableau operations that we're using as operations on these numbers, which will, it turns out, be tropical if you like the tropics. There'll be operations that can be defined in terms of maxes and pluses. And I'm not really going to talk about anything officially tropical today, but it is nice that the kinds of operations that one does are piecewise linear. And so I'm just sort of going to say that things are piecewise linear. Anyway, so in this representation, these entries kind of transform in a piecewise linear way under operations like the insertion operation. So we do this with this, and with the other half, we just do exactly the same thing. In this case, there don't turn out to be any threes because the shape of the 3, 2, and 1 tableau is the same as the shape of the 2 and 1 tableau. And notice that the 2 tableau wind up being the same shape because the outer shape, the total shape, is given by the main diagonal, which is shared between the two. Okay. So that's how reverse plane partitions correspond to pairs of semistandard Young tableau, and so that fills in this missing arrow here, and so hopefully, therefore, provides a bit of context for what RSK looks like, even though I'm not really going to describe it, though it's not that complicated. It's just there's again, starting from this matrix, there's a way to think of what you're doing with it as as an insertion process. Anyway, let me not say more about that. So the version of RSK that I'll be talking about, as I said, is really this one. And if we want to, kind of like I was saying, we can think about the left-hand side as being the lattice points I mean, so this is matrices, the m by n matrices of non-negative integers, but you can think about that. If you want to think about that like convex geometrically, you can just think about that as an orthant in ZMN, because there's going to be m times n many non-negative integers. So that's just geometrically, that's just an orthant. On the right-hand side, it's also the lattice points in a cone. I mean, the cone is the cone that's cut out by the inequalities that define a reverse plane partition. So, I mean, it's a more complicated cone. It's just these the various inequalities that define the property of being a reverse plane partition define some cone again in mn dimensional space. And again, the lattice points in that cone are exactly what we are considering as the reverse plane partitions. And it turns out that RSK is a piecewise linear map between these two cones, which restricts to a bijection between the lattice points, but it can be interesting to think in terms of convex geometry. And I mean, I know that Omri has thought about RSK in where some of the entries might not be integers, and so you can see from this description that that's a possibility. Okay, so my goal today is to give you a different perspective on this RSK correspondence using some algebra. And so what I'm going to describe in this section is what I call the algebraic stream. So this is just if you were just you're a happy algebraist and you sort of think, well, what could it possibly look like to prove RSK using algebra? So let's suppose that we have a category, and it's an additive category. So it's equipped with a notion of direct sum. So then we can say that an object is indecomposable if it isn't isomorphic to a direct sum of two non-zero objects. Okay. And let's suppose further that we have a category where every object admits a unique decomposition as a finite direct sum of indecomposable objects, and it's unique up to reordering and up to isomorphism. So in this case, the category C is called Kroll-Schmidt, and lots of categories are Kroll-Schmidt, and and finally, let's suppose that C has m times n many indecomposable objects. Well, then, if you want to think about an object in C, what data do you need to specify it up to isomorphism? Well, exactly a matrix, or exactly m times n many non-negative integers, because that's what which would represent the multiplicities of each of the indecomposable objects in the decomposition into indecomposables. There seems to be something in the chat. Let me just okay, so there was a question: do we know the number of components in the piecewise linear representation, meaning the number of different piecewise linear parts? I don't. I don't, but I'm not sure.
I think it can be worked out using Green's theorem. I mean, the
okay.
But it's complicated, I would say.
Yeah. I mean, it kind of has to be, because you're trying to transform this very simple cone into quite a complicated cone. Yeah, I mean, it's somehow like when you're doing that insertion process, when you insert like the different linear if when we were back, inserting, inserting 2, 3, 1, it would have worked exactly the same way if I just inserted 2, 4, 1, because all that was, so there's one linear zone. So we can bound the number because it's bounded by n factorial, I think, because no, sorry, we can bound, that's, yes, I guess it's bounded by n factorial. Because I think because it only depends on the relative order. Like if you think about what happened in the insertion process, only depended on the relative order. And so maybe each of the relative orders, no, there's probably some relative orders that wind up being the same. Anyway, I hope that clarifies that a little. Okay, so getting back to the Algebraic stream construction of RSK, the idea would be to find some category and find some other invariant on objects in the category, which naturally takes values in the reverse plane partitions, right? Because, so we've said, in this category that we're imagining, an isomorphism class of objects, if we think about it as
sorry, Hugh, the volume is going. I'm sorry.
Oh, thank you. Maybe I was pressing on. I see. I'm sorry. I had my hand over the microphone. I apologize. Okay. Should I repeat anything, or was it? Did you catch me fast enough?
The last 2 sentences, please, at least.
Okay. So we were looking at a category. So an object in the category, we can encode it just as the multiplicities of the indecomposable objects. So we can think of an object in the category as defining a matrix, an m by n matrix of non-negative integers, the multiplicities. But then if we had some other invariant that was naturally taking values in the reverse plane partitions, and such that two different isoclasses of objects would give you 2 different reverse plane partitions, well, that would prove RSK, and that would provide an algebraic version of RSK. So that's the idea. And so the rest of my talk is going to be explaining how we can actually carry that out. So to do that, I'm going to have to quickly recall a little bit about quiver representations, which is a lovely topic, which I really feel should be more widely known than it is. It's algebraically very interesting, and it's also very concrete. It's very easy to work with very explicitly. Anyway, I highly recommend quiver representations to anybody who likes sort of both algebra and combinatorics. So quiver is just an oriented graph. A representation of a quiver, just so we pick a field K, and then it's an assignment of a finite dimensional vector space to each vertex and a linear map to each arrow. So that, for example, if I had this quiver with 3 vertices and 2 arrows, I could assign vector spaces 0, a one-dimensional vector space, a one-dimensional vector space, and then so I need a 1-by-1 matrix to define this map. If I choose like a higher dimensional vector spaces, well, I need a bigger matrix. I can have multiple arrows, in which case, well, I need to assign a matrix to each of them. I can have loops as well. There's no problem. This is a very general sort of thing. 2 representations are isomorphic if you can obtain one from the other by a change of basis. And more generally, I should tell you what the morphisms are in this category. It's not crucial that you really retain this if it's not if this is like the first time you're seeing it, but sort of it's part of the contract that as an algebraist, if you introduce the objects of the category, you're also sort of contractually obligated to introduce the morphisms. So the morphisms, so if you have two and we always, in this business, we think of the quiver as being fixed. And so we have the category of representations of one fixed quiver. And then we want to talk about morphisms between two representations of that fixed quiver. So if I have two such representations, morphism from one to the other consists of a collection of maps from mi to ni, so between the vector spaces, same vertices. And so if that was all there was to the definition, it wouldn't be very interesting because it wouldn't really, I mean, that would define a notion of morphism, right? But it wouldn't be a very interesting notion because it wouldn't reflect the structure of the quiver at all. So what you actually do is you do that, but you also require that for each arrow you get a commutative square. So we have the maps coming from the representation associated with the arrow A going from vertex I to vertex J, and then we have the maps Fi and Fj, and this square has to commute. Okay, and so this category is a Krall-Schmidt category. So in particular, we have a notion of direct sum. So given two representations, you can define a direct sum at each vertex. You just take a direct sum of the vector spaces, and to define the maps, to map associated with arrow alpha, you just take you just think of it as you already have a map defined on each of the two pieces of the vector space that you direct summed, and so you just use those two maps on the two pieces. And so then we do have a notion of indecomposable representation. This is not crucial, but let me just mention it. So for this quiver, with two vertices and one arrow, there are three indecomposable representations. You could have this guy, you could have this guy, or you could have this guy. And the point is that this entry doesn't actually matter. Up to isomorphism, you could rescale this entry to make it any non-negative integer. So that's why, the representation where this one was replaced by a 3 or a 2.7 or whatever are all isomorphic to each other, because you can get from one to the other by rescaling, which is indeed the correct notion of isomorphism if you think about the notion of morphism that I defined on the previous page as well. So the puzzle is, what theorem of first-year linear algebra is this statement that there are three indecomposable representations for A2 for this quiver? What theorem of linear algebra is this equivalent to? Anyone want to take a shot? Someone asked if it's Krall-Schmidt even when Q has cycles and loops. So I think it is. I admit that I more normally avoid there being oriented cycles, but I don't think that there are reasons that one might avoid them, but I don't think that they cause a problem with anything that I've said. Anyone have a suggestion about?
Two matrices of the same rank, is that are equivalent?
Yeah, exactly. I mean, so said more concretely, any matrix can be turned into a matrix which has an identity piece and then is 0 everywhere else. Because basically what this is saying is so a representation of this quiver is a linear map between two vector spaces. That's exactly what the representations of this is. And then then what this is saying is that map, any linear map, can be broken up as a piece that corresponds to a kernel, a piece that corresponds to a co-kernel, and then a piece that is an isomorphism between there's an isomorphism onto its image. So So I need a notion of, I need to tell you what the indecomposable representation, oh, so let me just say, said that way, thinking about, this representation, the representations of the quiver with 2 vertices and 1 arrow, really representing any other quiver is sort of a generalization of, this very basic linear algebra. And so it turns out to be, anyway, so thinking, so you can by studying the story for other quivers, you can sort of generalize this basic linear algebra. What I'm going to need today is just quivers that are a path. So with some orientation. It's pretty clear that if you take a subpath like this and you put just one-dimensional vector spaces and non-zero maps between them, that you will get an indecomposable representation here. Because if you tried to decompose it into 2 pieces, then that would force you to get 0 maps somewhere. So these guys are indecomposable, and in fact, they're all the indecomposable representations. But that's a very special feature of the path. So in general, the representations of a quiver can be much more complicated. I'm not going to talk about that today. Okay, so here I just give an example of some other representation, and we see it decomposing as a direct sum of 2 indecomposables of this type. Okay, so let's actually try to see how we could realize the algebraic stream version of RSK. So I'm going to start with quiver with m plus n minus 1 vertices, numbered from 1 to m plus n minus 1. And then if I just took all the representations of this quiver, the number of indecomposables of that is the number of vertices plus 1 choose 2, because you just have to choose 2 endpoints, which could be the same for your subpath. So that's not exactly the combinatorics we want, because we want m times n many indecomposables. So we're going to take a subcategory. So the subcategory we're going to take is going to be direct sums of indecomposable representations, all of which are non-zero over some particular fixed vertex. So what we're doing is we're choosing a subpath where the left-hand endpoint is somewhere between 1 and n, and the right-hand endpoint is somewhere between n and m plus n minus 1. And as a result, there's n many choices for the left endpoint and m many for the right endpoint. So we have m times n many indecomposable representations. And in fact, there's more we can say about the structure of this category, which makes it clear why we should think of the indecomposables not just as being numbered, not just as having m times n many of them, but as in fact naturally occurring in a grid shape, so that it will make sense to think of the data of expressing a matrix as expressing a representation as a direct sum of indecomposables, to think of the multiplicities really as naturally forming a matrix. So the way that works is as follows. We say that x is less than y if hom x comma y is non-zero. Sorry, that should of course be x is less than or equal to y, since x has homs to itself. So this defines a partial order on the indecomposable objects. And the minimum is the projective at the vertex n. Sorry, I changed my convention and then I didn't change it correctly everywhere. So anyway, so it's the projective at n, and the maximum object is the injective at n, and the Hasse diagram of the poset is just an m by n grid. For people who have seen some of this kind of theory before, this grid is actually a sub piece of the Auslander right and quiver for this category, but for our purposes we can just say it like this. So this means that the representations, the indecomposable representations, kind of naturally come in a grid shape. So it's natural to, given an object in CMN, it's natural to describe its isomorphism class as really a matrix of non-negative integers.
Just to make sure I'm on the same page, the hom would always be one-dimensional if it were non-zero, right?
Yes, that's yes, that's right. Yes, that's exactly right. Yes. So now and this is sort of the meat of the idea. We need some other invariant of a representation, which is supposed to give us a reverse plane partition. So here it is. So this takes a little bit of digesting, but we'll have an example on the next page, I think. So given a representation, we can think about a nilpotent endomorphism of it. Okay, so that's going to be that's a linear map at each vertex. That's a linear map from that vector space of that vertex back to itself. And there's some compatibility condition on those different linear maps, but basically it's a collection of linear maps. So each of those is going to be nilpotent. So the whole thing is supposed to be nilpotent. So each of the linear transformations, the linear transformation at each vertex is going to be nilpotent. So it has a Jordan form, which has, all the eigenvalues are 0. So we can think about the Jordan block sizes as giving us a partition. So the theorem then is that given a representation, so at each vertex, we take lambda I to be the partition given by the Jordan form at that vertex. We do that, we could do that for any nilpotent endomorphism. We could find that partition, but what we want to do is we want to take a generic nilpotent endomorphism of this representation. It turns out that there is a well-defined generic behavior. So, which, a priori is not obvious, but anyway, it's true. There's a well-defined generic behavior. I should have said that I'm over an algebraically closed ground field, because if I were over like a finite field, then I'd be in trouble, because how do I even know what generic means? There's just like a finite number of options. So what do I mean? So I'm over an algebraically closed ground field, I should have said. So that means that it can make sense of this genericity assumption. Then you can take these partitions and enter them on successive diagonals of an m by n matrix. And this yields a reverse plane partition. And this defines a bijection from matrices to reverse plane partitions. We recover the actual RSK map if in the quiver, the arrows are all oriented towards vertex number n. If the arrows are oriented differently, we recover other RSK-like maps. So they're also bijections doing, from the same source and target sets. They're just different. So they were rediscovered very shortly after our paper by Duncan Dauvergne. He calls these other guys scrambled RSK. So that's, yeah, so anyway, there's the whole family of 2 to the n plus n minus 1. No, I guess 2 to the n plus n minus 2. Because you have a choice of each of the arrows, different maps. So let's look at an example. So here, this is an actual RSK example. So we have m equals 3, n equals 3. So we get this quiver. The representations that we're interested in look like this. And these arrows are the irreducible morphisms, which provide the Hasse diagram for the post set. So at the bottom, we have the representation that is just one-dimensional at the middle vertex and 0 everywhere else. That's the projective at this vertex, people who are familiar with these things. And at the top left, we have the injective at this vertex, which has full support. Okay, and so these are the, and so in the case where all the arrows are oriented towards the vertex n, it's somehow, it's very easy to see what the structure is of this poset. As we go up, we're just adding copies of k to the right. And as we go to the left, we're just adding copies of k to the left. And so we have this very simple poset. For other orientations of the quiver, you also get an isomorphic poset, but the identification of the vertices with the representations changes, and it's a little more complicated to describe. So let's start off with this matrix, we can, so these, so I happen to choose a permutation matrix, and according to the convention that I wanted to take, it turns out I should identify this as a permutation matrix this way, which I guess means that it's acting on the right on row vectors rather than on the left on column vectors, which you might have expected. Anyway, so we have this matrix. It corresponds to a sum of direct copies of representation, of the indecomposable representation. So this one here says we need one copy of the matrix in the bottom left. So that's here. This one says we need one copy of that guy, which is there. And this one says we need one copy of this guy, who's there. Okay. If we now want to look at the nilpotent endomorphisms of this guy, and you can think about that concretely if you like, just by taking the direct sum and writing down the condition of what it means to be a morphism and all that. You can do it that way. You can, however, also do it by looking at the quiver over here and seeing where the morphisms are among these objects. And what you see when you do that is that there's one non-zero morphism from the second object to the third object. And there's no other morphisms other than identity maps. And that allows you to read off directly what the Jordan form, a generic nilpotent endomorphism, looks like. So at vertex 1, what's going on at vertex 1? Well, it's actually just one-dimensional at vertex 1. So there's clearly only one Jordan block, and it's of size 1, and we put that in this diagonal. So we put a 1 in this diagonal. If we look at what's happening at vertex 2, we see that it's one-dimensional from this indecomposable, and it's one-dimensional from this indecomposable, but there's no morphisms between those two indecomposables. They're here and here in the poset, so they don't see each other. So again, it's just any endomorphism is going to be the zero endomorphism of this two-dimensional vector space. So it has two Jordan blocks of size 1 and 1. If we look at the middle vertex, though, so it's now three-dimensional, and we realize that because there is a non-zero map here, while there is, of course, always the zero endomorphism, which would give you 3 Jordan blocks of size 1 each, generically, you're going to make use of this possibility of having this map. So generically, what you'll get is one Jordan block here of size 1 and a Jordan block over here of size 2. And so that gives you this. And you carry on and you fill in these other entries. You can split this apart in the way that we described before to turn this into one standard, well, in general, it would be a semi-standard tableau here and a semi-standard tableau here corresponding to these two parts, because I happen to have started with something that came from a permutation matrix. I wind up with a pair of standard tableau, and you can check that this is actually the example that we saw at the beginning. So this map is actually Robinson-Schensted. But in general, what this map is doing is it's giving you Robinson-Schensted-Knuth. So there's also a way to think algebraically about how to invert the map. I think since I'm pretty much out of time, I won't discuss that. You can, of course, ask if you want to hear about it. And let me just mention a little bit about generalizing this. So the same idea can be used for other partition shapes. And that's we explain how to do that in our paper. There is a version of RSK that doesn't start with a rectangle, and so it's not going from, it's going from a shape lambda, from arbitrary fillings of a shape lambda to reverse plane partitions of shape lambda. So we can do that. You can also think about this for other Dinkin types, and that works well, and we explain how to do that in our paper. We are still working on extending this to affine types. It does work well, but anyway, we still have some writing up to do. In particular, it recovers results for Robin-Langer for affine AN, but it's this quite uniform construction in affine types. You can also think about these same ideas for other algebras. So a student of mine, Benjamin Dequesne, is thinking about this for gentle algebras, and you can also think about it for other kinds of subcategories in thinking cases, which he's also thinking about. Anyway, so that's what I wanted to tell you about. So thank you very much.
Well, thank you, Hugh. I guess we can unmute and clap. And now maybe let's just see if there are any questions. You can just unmute yourself and ask. Well, I have a question since while other people are thinking of their questions. So my question is this. So you said that once we figure out the Jordan types of these generic nilpotent endomorphisms, we have the RSK, the right hand side. So but then this means that the representation of the quiver up to isomorphism is completely determined by these partitions, right? Yeah. So in your paper, do you use the RSK to infer this, or can you prove it independently of the RSK?
I think we prove it independently. I mean, we have, as I said, we have maps going in both directions. I mean, it's a little, maybe it's a little bit.
Okay, so you have an algorithm to figure out.
But I mean, I mean, so our proof though is inductive. So it's sort of. I mean, so it's certainly not the case that we, well, yeah, so we don't, I mean, we don't sort of explicitly rely on the fact that RSK exists, but our proof is structured based on an understanding of what RSK, based on an instruction, based on, I mean, I guess sort of obviously, I mean, or unsurprisingly, let's say.
So there's no like really different perspective coming from, I mean, like you can't do it in a different way and then surprise yourself and say, oh, this is why the RSK must exist or something.
Well, I mean, the way that our, I mean, I don't know, I guess it's maybe a matter of taste, whether, I mean, somehow the way of building RSK that our proof is based on involves these operations on fillings that are called toggles. Anyway, so there's some like operations you can do on fillings which correspond algebraically to reflection functors. So there's some the operations that, I mean, reflection functors, which are like a well-known and well-studied and important thing that you can do in representations of quivers. Whereas these toggle operations, well, I mean, are a classic piece of combinatorics of reverse plane partitions, but are kind of like, you just write down a formula for, okay, we toggle and this involves like changing the entries in this funny kind of reflection-y way. So, is it more, I mean, so in some sense, I mean, reflection functors, you could argue that reflection functors are more natural than toggles, or at least reflection functors. So reflection.
I think I can't hear you anymore. Uh,
You're one of
yeah.
Hugh, if you can hear us, one of your things is frozen and the other is muted. Oh, but his other camera he's muted. He has turned off the volume on the other, so he can't hear us.
Seems like he can't hear us either. So yeah, we couldn't hear that last bit. We couldn't hear the last bit of what you said. Hello. Can you hear us? It's yeah. It seems like he can't hear us either. So one of his computers is, I think.
I think he's reading what the messages are, hopefully.
Great. Am I audible again?
Yes.
Oh, super. Right. Yes. Sorry, I don't know what happened with my other machine, but anyway. So
we didn't catch the last. Yeah.
Yeah.
Okay.
So the RSK itself can be completely reconstructed in terms of using Green's theorem. You know, the shape is given by Green's theorem, and if you look at the shapes given by different subsets of the words, just the letters 1 and the letters 1 and 2. Is that how it goes? Yeah. So the you can actually characterize the RSK in terms of Green's theorem, and the point is, this is one way of thinking of it as a piecewise linear map. I was wondering if the scrambled RSKs also have some similar Green's theorem, and or maybe there's some other way of making them piecewise linear or tropicalizing.
Well, I mean, they certainly are piecewise linear.
How do you see that?
Well, yeah, I mean, I guess it's not. I guess it's not obvious from the description, but I mean, I think it's unsurprising that the to determine what a generic nilpotent endomorphism will do is somehow not is not sensitive to changing the multiplicities if the multiplicities maintain the same order. I mean, it's the same kind of reason as for yeah. So I mean, if you have two indecomposable representations that correspond to two different matrices, but the relative orders of the entries in the matrices are the same, then they will then you'll get this then the same linear map, then RSK will be realized on those two things by the same linear map. Yeah, that is to say, they'll be in the same domain of linearity. Because in fact, you can see what the, I mean, so in type A, this question of what is the generic nilpotent endomorphism is actually
it's easy to see that is, or I mean, that turns into really a statement about combinatorics and recovers another version of RSK which I think is originally due to Gansner, where you think about, you know, your entries in the matrix, and then you ask, you know, what is the path through the matrix such that the entries have such that the sum of the entries is maximized, and then what is the union of two paths such that the sum of the entries is maximized, and so forth. And so you ask a bunch of questions like that, and that's another way to formulate.
That's for the RSK, right? But what are these paths for the scrambled RSK?
It's really the same. What's different is, so in RSK you do that for the whole matrix, but then you also do that for
you do that for segments, right? Like
segments of the matrix, yes. And so the point is that in the scrambled RSK, the way you choose the segments is different. So which segments get used is different. So that instead of, so I mean, I think that for regular RSK, you're using segments that are
maybe upper left subrectangles. Right?
Yeah, or upper left or bottom right or something. And so but it turns out that in these other versions, you start to lose, you lose things from both the left-hand side and the right-hand side, and from both the top and the bottom.
Okay. Yeah, I also had a silly comment. I think you don't need to use algebraic geometry to define generic. You can just talk about maximal with respect to refinement.
Yeah. Okay. That is in fact true. I mean, but then, I mean, you need to talk about algebraic geometry to justify the fact that there is a maximum.
Okay. Yeah.
Well, I mean, why is there a maximum? There's a maximum because that's what's obtained generically.
Okay. Yeah.
But I mean, you're right that if one just wants to say the thing, one can say it without using algebraic geometry.
Okay. I guess others. Do others have questions?
Actually, Hugh, I had a question about the sort of general situation.
Mm-hmm.
So am I right in understanding that in general, you're going to have some piece of this Auslander-Reiten quiver, which you're going to decorate with multiplicities? It might not be a grid anymore. It might be something complicated. And then somehow finding this maximal endomorphism is implemented by some toggling on this.
Yeah.
It will be a poset, right?
Yeah.
So, okay, so that's like one part of your RSK, but will you in general have a second step of this RSK which splits it into two objects that are like semistandard tableau? I mean, what plays the role of semistandard tableau, when I move away from this grid case, say, suppose right. I'm doing type DN, I don't know.
Yeah, so no, there isn't a splitting. So it's really generalizing the formulation in terms of reverse plane partitions. And I should I guess maybe say that the way that we do it involves a choice. I mean, so as in type A, there was somehow it was important to choose a vertex of the quiver. So because we looked at all the representations that were supported over that one vertex, and we wouldn't have gotten a bijection in this way if we hadn't have made that choice. Though my student is looking at sort of what you can do with more general kinds of subcategories, but you can't just take the full subcategory. Well, you can take it, but if you do, then RSK isn't bijective anymore. So you have to pick a vertex, and the way that we do all this, well, and again, somehow things start to break down if the vertex that you choose is not minuscule. So you can choose any vertex in type A, but in type D, you have to choose one of the leaves of the Dynkin diagram. In E6, you have to choose again, one of the leaves that's further out in E7, you have to, there's just one leaf that works, and there's no vertices in E8, so you can't do it in E8.
How about have you done this in the pre-projective case? If you take pre-projective type AN, is there and you choose a vertex, there your supply of modules will be much richer, because you'll have, in this Leclerc setup, basically you take any partition which is supported over the vertex, you have a big supply, and imagine a very complicated.
Yeah, we thought that there should be a connection to pre-projective algebras, and we couldn't make that work. I have some work with Stephen Karp, which will be in a paper which is coming out soon, which has in it both a version of RSK and pre-projective algebras, but it's a little bit different. It doesn't connect up to this, or at least we don't know how to connect up to this. I mean, I thought it would connect up, but it doesn't anyway. But so there is a pre-projective algebra RSK story, but for that, I'm afraid you have to wait until, well, there's a version that's on the archive that was a FIPSAC abstract, but the long version should be coming out very soon.
Thanks.
Raghavan had a couple of questions, so I'll just ask them here. It just probably overlaps with something that already has been talked about. So 2 questions. One was, first, in other Dinkin types, is what you get already known in some form, or is it new? And secondly, does this algebraist's viewpoint explain in some way the piecewise linearness?
I think it does explain the piecewise linearness. I mean, yeah, I think so, because you can see why calculating this generic nilpotent endomorphism isn't sensitive to, or is sort of you can reformulate it as something that is clearly linear on restricted to regions where the entries have a fixed order. So yes. For other Dinkin types, it's so in type D, it's not substantially different. I mean, it's a little bit different. It didn't seem to have been formulated in exactly these. Well, it certainly was formulated in exactly these terms, but it's like a tiny bit different. It somehow the interesting case in type D is when you choose a vertex that's one of the 2 antennae of the diagram, and then what you get is a map between arbitrary fillings of kind of a triangle-shaped poset and reverse plane partitions of a triangle-shaped poset. So it's kind of like a half of the diamond that we were seeing in type A. And you can, by unfolding the half diamond to an actual diamond, you can recover, or you can get back to kind of regular RSK. So it's some kind of RSK plus a symmetry. That's certainly understood. That is most naturally what you get if the orientation of the 2 arrows going to the 2 antennae are the same, and if they're different, you get something that's like different in a certain way, but there's a way to it's not so different. I don't know. I was a little bit. I was hoping for something more more novel than it turned out to be. So the type D is not so different. So far as we know, the type E6 and E7 cases are not something that people had studied before. And I guess it's a question about how excited you get about E6 and E7. Possibly more interesting is what's going on in an affine type. Again, we have this because they're E6 and E7 are still special cases, but they are kind of infinite. So it's maybe more interesting. And the other types are, and it potentially seems more exciting to have a uniform approach to all the affine types where, things are infinite enough that it can be a little hard to work with without, where, I have the feeling that a little bit more theory might actually help people understand things a bit better.
There's a question on the chat which I'm really intrigued about. So Vishwanath asks if the dual RSK can be interpreted in this way.
Yeah. This is the one where you have a matrix that's like a 0-1 matrix?
A 0-1 matrix, and you have semi-standard Young tableau of mutually conjugate shapes.
Okay. I don't know how to do that. It would be, I don't know. It's not, on the face of it, it maybe isn't so promising because, the part of the point of the sort of algebraic dream that I presented was, the idea that, the objects on the left-hand side are clearly want to be encoding, Carl-Schmitt decompositions of object in an additive category. And, that's not true for 0-1 matrices. Of course, you can think of 0-1 matrices as, a subset of integer matrices, but then you've sort of forgotten like why you were thinking about them in the first place. So I don't know. I would love it if I knew how to do that. I'm not sure it's the most natural thing to hope for.
Certainly seems like it would need a new idea. Maybe something exterior algebra or something.
No, but from
that's
this
true.
point of view, are these multiplicity-free decompositions somehow? You could think of a 0-1 matrix potentially as a sort of a multiplicity-free decomposition, right? Since everything occurs at most once.
Yeah, exactly.
So are such objects somehow natural? Could they be natural in this setting?
Not that I'm aware of. Certainly you could do that, but algebraically it's not. You can obviously say that you say I consider the set of objects of that form, and there is a set of objects, but I don't think that's something that would occur naturally to a representation theorist to want to do. Typically they like additive categories where you can take direct sums, and and so this would just be some set of objects within an additive category. The idea that there should be some kind of exterior algebra in the story is more. That's more enticing, but I don't have any idea how one would actually do that.
Well, any more questions? All right, so if there are no more questions, then we'll stop the official part of this seminar. Thank you, Hugh, again. It was a really nice, beautiful exposition. You made it look really simple. So thanks a lot.